Today I'm going to be exploring the house edge and theoretical winning percentage of different playing strategies in the popular card game Blackjack. Blackjack is a popular casino card game where the goal is to get your hand's total value as close to 21 as possible without going over it. Each player is dealt 2 cards, and the dealer is also dealt 2 cards with one face up and one face down. Number cards are worth their face value, picture cards are worth 10, and aces count as either 1 or 11. On your turn, you can either hit, which is to take another card, or stand, which is to keep your current hand. After all players have either stood or gone over 21, the dealer reveals their hidden card and must draw cards until reaching 17 or higher. Whoever has the highest hand under or equal to 21 wins. Blackjack as a game is quite simple, but when you start trying to calculate probabilities, it becomes infinitely complex, considering in just the initial deal, which is the player's 2 cards and the dealer's 1 shown card, there are 66,300 possible combinations using just one deck. So if I wanted to determine my probability of winning any given game of blackjack, I have to use a technique called Monte Carlo simulation, which I will now explain. If I wanted to calculate the probability of flipping a coin and it landing on heads, there are 2 ways I can find it. The first way is to count that there are 2 sides to a coin and use simple logic to say that there is a 50% chance of flipping heads. The second way is to flip the coin many times and tally the number of heads I get. The more times I flip the coin, the more accurate the estimation will be. This is called a Monte Carlo simulation. Here I have some simple code which allows me to simulate thousands of coin flips at a time. If I run the code and simulate 10,000 coin flips, you can see our percentage is a lot closer to what we'd expect at 50%. So using Monte Carlo simulation, I will be able to test and find the statistical best blackjack strategy by simulating thousands of games and comparing their corresponding house edge. To do this, I will need to code an automated simulator like I did for the coin flip. When building a blackjack simulator, I'm going to have to instruct my simulation player on how to act in every possible situation they are dealt. I can do this with 3 main tables. These 3 tables will form the basis of my simulated player's decision making and strategy. The first table is the hard totals table, which covers situations where the player's hand doesn't contain an ace counted as an 11. The second table is the soft totals table, where the player's hand includes an ace counted as 11. The third table is the pairs table, which instructs the simulator on which pairs I want them to split on. These tables will instruct my simulated player on what to do in every single situation. Initially, I filled these tables with how I would play each hand. Implementing them into my simulator, this is what they look like. One thing I need to consider when building the simulator is that it is commonplace for a casino to use 6 to 8 decks at a time instead of just 1, and also place a cut card to decide when to reshuffle the decks. I have implemented 6 decks into the code, with a cut card being randomly placed in the back half of the chute. Here we have the finalized blackjack simulator coded in Python, and it could simulate thousands of games at a time. I've instructed it to just bet 1 imaginary chip per game, and once it completes the simulations, it will print a final report. This version of the code uses the strategy tables that I made. Let's see what happens when we simulate 100,000 games. As you can see, the simulator had a net result of negative 7,233 chips over 100,000 games, with a win percentage of 42%, a loss percentage of 49.3%, and a push percentage of 9.1%. We will also need a way to measure the success of our different blackjack strategies. This is where expected value comes in. Expected value tells us on average how much we win or lose per bet over the long run. To calculate it, we take our total net chip gain and divide it by the number of games we played. To convert this into house edge, we just turn it into a percentage of the original bet. Adding these simulation results into Excel, it's clear my self-made strategy tables are not profitable over the long run. With an expected value for every dollar bet, 7 cents is lost. So I did some research to find out what perfect blackjack play actually looks like, and as you can see, there are big differences between my self-made strategy tables and the perfect play strategy tables. mainly in their use of doubling and splitting. Who would have thought that splitting twos is actually considered optimal in some situations? Here we have the perfect play strategy tables implemented into our simulator. Let's simulate 100,000 games. As you can see, we have a win percentage of 44.2%, a loss percentage of 49.3%, and a push percentage of 8.6%, with a net result of negative 3,564 chips. Adding these results into Excel, with the perfect play strategy table, win percentage increased by just over 1%, with loss and push percentage decreasing slightly. However, the net chips lost is almost halved, only losing around 3.5 cents for every dollar bet. This must be due to the increased amount of doubling and splitting in the updated strategy tables. This can be seen with an extra 1,700 hands played due to splitting. So this means even with the most optimal blackjack play in every single situation, blackjack is a losing game, with a house edge between 3 and 4% with perfect play and 7 to 8% with amateur play. This study I found claims a house edge of around 2%, which is not far off my 3 to 4% considering a Monte Carlo simulation only provides an approximation. I'll link this study in the description as it's also where I got my perfect play strategy tables from. However, there is one more variable a player can change in order to try and gain an edge over the house. This variable is bet size. After every game is played, the player can change the amount of chips they would like to bet for the next game. If a player is somehow able to determine which games they are more likely to win, they could increase their bet size in those situations and decrease it when the odds are worse. This is exactly where card counting comes in. Card counting is a technique that tracks which cards have already been dealt to estimate the proportion of high cards, like tens and aces, still remaining in the deck. When there are more high cards left, the player has a higher chance of getting blackjacks and strong hands, while the dealer is more likely to bust. By keeping a running count and converting it into a true count, which adjusts for how many decks remain in the shoe, players can predict when the conditions are most favorable. This allows for them to strategically raise their bets only when the advantage shifts slightly in their favor, reducing the house edge and over the long run, potentially turning the odds into a positive expected value. It's important to note that while card counting isn't actually illegal, casinos strongly discourage it. If you're caught using this technique in a real casino, they can refuse to let you play blackjack, ask you to leave, or even ban you from the property altogether. So I'm definitely not recommending you try this in a real casino environment. These simulations are just purely to determine how much your expected value and win percentage change when card counting. I've implemented the high-low card counting system into the code to keep track of the running count. Every time a card is dealt, it updates the count by adding 1 for low cards, subtracting 1 for high cards, and ignoring neutral cards. Then, to get the true count, it divides the running count by the number of decks remaining in the shoe. This true count can help decide how much to bet. Higher counts mean more big cards are left, so the bet size increases, while low or negative counts reduce the bet. So here we have the finalized code with card counting implemented alongside the perfect play strategy tables. Let's simulate 100,000 games. 100,000 games, with card counting to change the bet size, we still end up with a negative net result of negative 7,940 chips. However, if we consider the games where the true count was greater than or equal to 1, we end up with a net result of positive 6,640 chips in 24,727 games. Adding these simulation results into Excel, it is clear that win, loss, and push percentage remain unchanged. However, due to our changing bet size, when true count is greater than or equal to 1, there was an expected value of 0.27. Meaning for every dollar you bet, when the true count is greater than or equal to 1, you gain 27 cents. So therefore, the most optimal blackjack strategy for turning a profit is to only play when the count is high. This is why when card counting is done successfully, either in real casinos or in movies, the players work in teams, with counters on lots of tables and a high roller who bets large only on the tables with a high true count. Thank you for watching. If you would like to test your own strategy tables and see what your win percentage and expected value is over thousands of games, I have left a link to the GitHub repository of the code in the description.